Good evening. Welcome back, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to combine a little math and physics and see if we can get that to equal a gold medal winning combination. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make those tough to teach, tough to learn concepts accessible to all my students. Tonight, we're really excited to be joined by our two panelists, Todd Grabba and Brad Poznanski. Todd is the STEM division leader at Crystal Lake South High School in Crystal Lake, Illinois. His teaching background is in physics and chemistry, but has extensive curriculum experiences in all high school math and science practices. Todd's main professional development areas for TI are in using the Nspire and Navigator systems in science classes, and incorporating coding into the classroom or STEM activities with the TI Innovator Hub. Todd, it's great to have you with us tonight.
Happy to be here.
And Brad is in his 25th year of teaching at Comsowog High School. He has been using TI technology in his classroom ever since he student taught. He's a firm believer that you never stop learning, and that is evident in his pursuit of new and innovative challenges made possible through TI technology. Brad's presented at a lot of local, state, and national, as well as international conferences. He coaches 3 varsity sports, and just like all of us, he loves to sail in the Caribbean. Brad, it's great to have you with us tonight.
Glad to be back, Michael.
At this point, Brad is going to talk through our agenda.
Welcome, everybody. I do have to say a happy birthday to Michael Houston. I believe it was his birthday yesterday, so I just wanted to pass that along.
Thank you.
Webinar attendees.
Taking a bow.
All right, tonight we're going to have a little fun. I'm not sure if everybody's aware, but there's some international competition that's going on in Japan these days. We waited over a year to see it, and we were going to do this webinar last July, and now we're finally able to do it live for you guys. So we're excited about being here. We're going to be using some of the TI technology to analyze data from different athletic competitions. Could be anywhere from swimming to track and field, or a couple of the ones that we're looking at. We want to apply the different features of the TI-Nspire as well as the TI-84CE and how you can use them in your classrooms, give you guys ideas. Also to collaborate on additional data sets, ways to analyze data. We're here to give you guys some inspiration, some ideas to use in your classrooms that you can take away, use with them this fall, and we're really excited about that.
Awesome, Brad. Thanks so much. And Todd is going to discuss our expected outcomes.
Yeah, so hopefully by the time we're done here, we probably have more put together and we'll be able to share. But hopefully everything we get through will help show how you or students can analyze data sets in multiple different formats across different platforms, how you can use the technology available here to organize and analyze data, and then also how you can use mathematical modeling to make logical conclusions and predictions, whether you're in a math class or a science class or a STEM-based. We're trying to integrate everything into.
Todd, thanks so much. Tonight we're expecting a large crowd, so your audio is muted. Feel free to send any questions to Brad or Todd using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the event. With that being said, Todd, let me pass things over to you.
All right, thank you, Mike. So WebEx is not my forte. Zoom is something I got to learn pretty well last year. So we're going to do our best to make it through this different technology and share things appropriately and correctly with you. So hopefully everything works here. And also my 3 children and dog will leave me alone in here so he can present without interruption. So that's the goal here today. We're going to start off with sharing the screen here and going through we're going to bounce back and forth between a slideshow that we have put together and then also some TNS files and 84 files to help show a variety of different ways that you can analyze this data and put this information together. So again, math plus physics equals a gold medal combination with Brad and I as the hosts for today. There's our contact information in a variety of different ways. Both of us are a part of the T-Cubed community and looking forward to hopefully interacting with all of you both tonight and in the future. If you have any questions for us about what we've gone through tonight, or if you have suggestions of ways that other data sets that we could use or ways we could analyze it, we'd love to learn from you as much as hopefully you're going to learn from us here tonight. What we're going to talk through today and some other things that are beyond what we're going to talk about, but looking at some easy connections that can be made between math and physics and can be analyzed either in both classes or independently in either one. Would be the swimming competitions that have been going on so far in the competitions over there in Japan, and it's been pretty fascinating to watch those. Talk about running and sprinting specifically is what we're going to take a look at tonight. We're also going to get into projectile motion and parametric motion that would be modeled in projectiles. And then some other areas we're not going to be able to get into, but areas that Brad and I were brainstorming would be other great connections to be able to make would be things like the pole vault, which Brad was a pole vaulter back in the day, and so he knows quite a bit how to do it, or quite a bit about how to do it. But we can also look at the various transfers of energy, the velocity changes, what happens from the chemical energy inside your body all the way through the changes in potential and kinetic energy, the elastic energy in the pole. All of those can easily be looked at and analyzed, along with things like rotational kinematics and dynamics. This picture was made available recently on Twitter, and just an incredible athlete and a lot of courage and bravery in everything that she does. But just the photography of this was also amazing. So there's so many areas that we can begin to explore and dive into. But one of the things that we want to do, and we talked about before, is making this interactive. So the first thing that I would like to do is actually open this up for some chat on the side here. And one of the things to get students thinking in a classroom is just to present them with some information. It doesn't need to be tied to the curriculum, as long as we're getting them thinking, because it's priming the pump to then allow them to think about the curriculum down the road. So I got this from Sports Center on Twitter today. And what I would like for you to do over in the chat window on the side is to take a look at this and maybe rank your top 5 from this list, your top 5 countries based off of their performance so far, and a little justification of why. I'll give everybody a minute to take a look at that. Don't forget that second part. Just a little justification as to why.
You could also use the reasoning that your students might use.
All right, so thank you to those of you who have put your guesses out there. As you can see from the window, there's a variety of different ways that people are ranking these, right? And it's most gold medals, most even distribution, most total medals. There are any way of looking at these, and none of them are wrong, right? And so what we want to be able to do is, that's a great question. Is there inconsistencies? We want to get kids looking at information. We want to provide them with some data that is readily available, that is relevant, that they can use to then start to think about different ways of analyzing this. And what are some advantages maybe that they can have by different motions they can do and different ways that they can train and all kinds of different things that can be brought into this. And so obviously we're using this time to know, good, what's the density? How many athletes are on each team? USA has 330, but how many does does Great Britain have? I don't know that answer, but there's great ways to look at it. So we want this to inspire other data sets then that students would want to look at. Get them thinking about, you know what, I don't really care about the sports that are going on right now, but I'm interested in this. So how can they pull that data set in? And so now we're starting to meet kids where they are, make it relevant and meaningful for them, and get to our ultimate goals of having them analyze the data. So thank you to everybody who participated in that.
So Todd, just jump in for a second. So, I like the fact that some people were asking about the weighted system. So Michael did mention that I coach some sports, and one of the sports I coach is track and field. And so the weighted system there's point values for places. First place might be 10 points, second place might be 8 points, and so on. So it'd be kind of an interesting thing possibly to be able to graph that and see what, different weighted systems would be as far as straight, total medal count versus the weighted system. Absolutely.
And so it's great to be able to start with some of this information, then take input from your kids, and then, all right, well, how can we easily transform this information into that weighted system, and how does that change? So lots of different areas and things that we're going to get into tonight. So again, great way to get started there. Thank you for all your input. And now let's start actually looking at some of this information. And so we're going to jump into some different athletic events. And the first one that we're going to talk about is swimming. And what are some different ways to analyze swimming, and what's important for a swimmer to be able to do. And this is a very simplified approach. There's lots and lots of different things that swimmers need to be able to do to be highly effective as swimmers. But we're going to take a look specifically here at the drag in the water and how changing the drag coefficient can make you a better swimmer. And one of the ways that I think is great to analyze this is going back to 2008. And there was a dramatic race in the 100-meter between Phelps and Kavic. And Phelps, obviously, from the American squad, Kavic from the Serbian squad. And Kavic was leading the race, coming in close. And so this is going to be a frame by frame of the end of this race coming in to see who's going to end up winning this. So it kind of goes slowly through the different frames. But here they are about 1.5 meters away from the wall. Next frame, and Kavic is clearly well ahead of Phelps. Coming in closer now, Kavic is trying to coast in with that last push of his, and Phelps is trying to get one more butterfly in. Kavic is still coasting in, and he's raised his head up while Phelps is coming down into the water and got his head down. And right at the last second, literally the last 100th of a second, Phelps came back and won this race. Anybody watching this race with the naked eye from the cameras above thought for sure that Kavic had won. The announcers thought that Kavic had won. But when the timers came back, it turns out that Phelps was 100th of a second ahead. And so what is it that can make this difference? And what is changing between these two athletes that allowed Phelps to make this dramatic comeback right at the end? He does have super long arms. He's 6'4", but he's got the wingspan of a person who's 6'7". He's got double jointed shoulders and hips, and so he can elongate his body in ways that others can't. His hands are enormous. His feet are huge. They're like extra flippers in the water. But Kavic has this bodysuit on, and this bodysuit was actually banned 2 years after this race because it allowed there to be such a dramatic reduction in the drag of the racers. So how does all of these different things matter in terms of what's going to happen in the actual race itself? So how can we analyze some of this and what the impacts of that are going to be? Well, one of the ways that we can do that, and I'm going to show this screen and then jump into the Nspire emulator, is by having the Nspire do some calculations for us. And Stacy, thank you for the enthusiasm. I'm actually married into a Serbian family, so that race between the American and the Serbians was very highly contested in our family, and it's still something that we argue about 12 years later. So math boxes is a way that we can put in some information, store some variables, and have it do some calculations for us. And so let's go ahead and jump into that. I created a notes page first, and I just inserted the image from that video. I just took a screenshot of it. Put it in here. That's an open source video on YouTube. And then I created, again, it's a notes page, and on notes pages are where you can insert the math boxes. So I started this with just defining what some of these different variables are. And there's a physics professor. His name is Rhett Aline, I believe is how it's pronounced. At the bottom of this page is a link here to an article that he wrote that I was able to then pull from this. He's also a very good person to follow on Twitter, lots of very good examples of what he does. So this article here is linked if you want to go back and take a look. But from his article, he talked about how drag impacts the velocity of the racers. And when you're getting to the Olympic level, the racers all have such similar characteristics that there's very minute things that can change that can impact the race, like we saw at the end of that race there. And so as we're talking about showing kids things ahead of time to get them excited, in science with the NGSS, we talk about having phenomenon to start lessons. That YouTube video is a great phenomenon to start analyzing this information. What difference does it make? So this equation here is the equation to use to figure out how the velocity changes based off of the drag coefficient. And so then I created math boxes that are in here for all the different variables that go into that equation. And so to do that, the simple way to create a math box went in a notes page, if you haven't done that before, is you come up here to menu, insert a math box. In a science class, you can also insert a chem box. And so within the chem box, you can put in superscripts and subscripts to donate the charge or the amount of particles that are inside of a molecule. But for a math box, you can either put in equations like I had before, or you can put in any variable that you want, and you can store that variable as some value, and that variable will then be stored the rest of the way through. Now, I don't want to have that in there, so I'm going to get rid of that for now. But that's how you would insert a math box into whatever page you want to do. So I went ahead and did that already. And then what I did is I created the same equation. So here's the basic velocity equation that we had up above. And what I have is the density of water, the area, the power of the swimmers, all of those are set as 1. And here's the drag coefficient. And now what you can do is if that drag coefficient changes, if you have the exact same drag coefficient, you can see that the velocities then are going to be the same. So then we can calculate the change, and they're going to be the same because everything is the same between these racers. Well, what happens if you can reduce that drag coefficient to be 99% of what it originally was? Well, now by changing this in the math box, it changes that variable inside this equation, and it shows that this velocity, now the ratio of velocities is just slightly higher. By having that 1% reduction in drag coefficient, that racer is now 0.34% faster than they were. Now, what does that matter for anything? Well, what that does, I should have deleted this. Darn, that's going to mess things up. Anyway, what that does for us, let me go back and see if I can change some of these.
Todd, let me just interrupt you 1 second because it's a beautiful transition, or not transition, but to work off your velocities there. I was watching a couple races just recently, and on the television, NBC has, as the swimmers are going through the water, they're showing their meters per second velocity as they're racing. So what you have right there is being displayed in real time on the coverage of the swimming event.
All right, so got this back. Thanks, Brad. I got this back to where it was. So that 0.34% faster doesn't seem like it makes that big of a deal, right? We reduced the drag coefficient by 0.01%, or by 1%, right? Well, what that does is makes the racer 0.26 seconds faster in 100 meters. That 0.26 seconds makes a dramatic difference when you're looking at the race that we just showed. And so with these math boxes, you can easily go through and change, all right, well, what if we reduce this drag coefficient by 2%? Well, now how much faster am I, and what's the time difference? So now you can start looking at, well, what impacts drag coefficient? And as you go back to the race and you look at this image, I was talking through a variety of things ahead of time to look at. And I said, well, you can see that Kavic is just trying to coast in. Phelps is getting that one more push as he brings his arms around the one last time. But then I point out that Kavic has raised his head up. Well, when he raised his head up, that reduced his dynamics through the water, whereas Phelps was more aerodynamic or fluid dynamic in the water. That reduced his drag coefficient related to Kavic and allowed him to go faster through. Now you can take these variables and you can store them as you go through, and you can capture these variables. So with the new velocity, I can capture this now on a spreadsheet, and do data capture automatic, and the new velocity I had stored before as V1. And so now if I want to go back in here and change this velocity from the 0.98 to 0.97 drag coefficient, that changes V1, and on my spreadsheet, it's now captured that information. So I can now take this information on the math page, I can store it onto a spreadsheet, and if I'm storing multiple variables, I can now create a graph of those variables that I stored from the math page. So multiple different ways that we can go through and start analyzing, dissecting the information and having multiple representations of the same information that we were looking at before. So you start with a phenomenon, you get the kids excited, you present them with some data, and then you start looking through the analysis of that data. And then if you're, again, in a physics classroom, you can start looking at, well, what are different ways to reduce that drag coefficient? Dennis pointed out also looks like different swimsuits. That's exactly a major benefit that Kavich had. And one of the things that I pointed out again in my intro spiel is how Kavich has this bodysuit. That bodysuit reduces the friction in the water, causing him to be able to swim faster, giving him an advantage, an unnatural advantage over Phelps, because Phelps doesn't have that upper body suit on. And why it was banned in 2000 by the international competition, because it was creating unfair swimming advantages. So a fun way to go through and take a look at swimming analysis and using multiple different technology features, using math boxes, spreadsheets, graphs, and a way to bring in the relevant information that we're now able to see on in the competition that's happening. If you are not familiar with the TI website, there are a variety of pre-created activities. And Brad found this, I believe, today. But this was on the TI website. This is actually an activity for the 83 and the 84. But it was an activity that was designed to look at the times of swimmers based on these bodysuits. And so just like Dennis brought up, the bodysuit seems to be something. There already is a pre-created activity to analyze how these suits impacted the times of the swimmers. So all of this is already out there and created and ready for you to go. Brad, let's transition into running.
All right, so one of the premier events in track and field is 100 meter. That's always, determines the world's fastest person, whether it's the female race or the male race. That's going to be the one race that everybody's watching highly. So there's a link that we have. It's from the New York Times, and they ranked every runner, whoever ran the 100 meters in the Olympics, and showed where they'd finish relative to one another. All right, so it's kind of a neat intro activity. All right, just like Todd had that little video to kind of like to hook the students, to have them watch something and start thinking about it and generating questions. All right, same thing here with this video for the 100-meter dash throughout history. All right, so what we're going to do is we're going to do some analysis of those 100-meter dash times, and also the whether it's going to be the world record time for women or men, also for the 100-meter gold medal winner throughout history. And we have a couple activities that we're going to do to analyze that, generate some excitement and predictions as well. So we're going to be checking those out. So we want to take a look at the data that is available. All right. So, that's one nice thing about athletics is they have just tons and tons of data. It's a matter of fishing it out. So a couple of things that we're going to analyze here are going to be the world record progression, how it's kind of progressed over time, the winning times in the competition that happens every 4 years, the kinematics. All right, Todd's going to go into that with a bunch of the physics. And we're going to analyze split times. All right, the 100-meter dash is so precise and so fractional of a second that they actually time every 10 meters. So we're going to be looking at some of those statistics as well. All right, here you have a picture, I believe it was in 2008, of Usain Bolt winning the 100 meters. Kind of amazing that as fast as all these humans are, he was that far in front of everybody. And when you look at the time on paper, it doesn't look as big of a margin, but it's phenomenal how he was able to kind of look around and take stock of everybody around him as he's crossing the finish line. So that was such a great photo right there. All right, so here's some times. Now, just for, I guess, put things in perspective, The reason why we're using from 1968 on is because they had automatic timing, right? So this was a camera timer, so it's the most precise timing that's available versus you go to a high school track meet, a lot of times they're using a handheld stopwatch. So this is the precise times of all these athletes throughout the years, right? So we're going to plot these using the data here, right? So we're going to enter these into the calculator. So Todd, if you give me control, I'm going to use those, right? So here they are actually in the data.
Yeah, and let's transfer this over to you now so you can show how to do this on the 84.
Excellent. All right. So I'm going to share with you my smart view here. So there we go. All right, so what we're going to do is we're going to enter that data into a list. All right, so you're familiar with the 84. We're going to press stat, and then we're going to use number 1 for edit. All right, this is where we're going to put all that data. All right, so depending, this is not a huge data set, so it's definitely doable for your students to be able to, if you had a worksheet or that data that was on, put it on an overhead projector for them to see, and they could enter it in there. Make sure that they double check the data, all right, that all the entries are correct, all right, because it's very easy to do a mistype one of those, all right? So in L4, we have the women's year of the world record being set, and in L5, we have the women's world record time. In L6, we have the men's year that the record was set, and in L7, we have the men's world record time. All right, so what we're going to do is we're going to take a look at them. We're going to see a scatter plot of these, right? So hit second, y equals, we're going to turn a scatter plot on. I'm going to choose number 2. All right, I'm going to turn it on. And we said that list 4 was the year, and list 5 was the time for the women's world record, right? And I see that. Why were there 2 world records? It was just a progression. They give them credit for if they tie the world record. So if multiple performances were the same time, they get credit for holding the world record. So that's the reason why there might be multiple at the same time. All right, so now if we want to plot this in a nice efficient way, if we press zoom and number 9 for the stat window. Also, you could actually have your students try to think about what's the window size going to be. All right, sometimes I will do that as well to say, hey, what's our domain? What's our range of values? All right, so I'm going to choose number 9. And we get to see a progression here. All right, so now here we can take a look at this and say, hey, what do you guys notice? All right, and hopefully we get a bunch of comments where, what do you guys notice about these times? Are they increasing or decreasing? All right, we don't have any labels on the axes here, but we can see, hey, listen, this is progressing pretty well, and they're decreasing in times. And we could include all sorts of things. Is technology increasing? All right, maybe they're getting a little bit better sneakers or shoes. All right, are the tracks getting faster? All right, so little track knowledge is the harder the surface is, the faster the track is. So for a 100-meter runner, they want the track very firm. For a distance runner who's going to be doing multiple laps, they might want to soft the track because that's a little bit better for them. All right. So those different factors. All right. So as Todd was doing with the swimming, his swimsuit made a difference. All right. And then they outlawed it in year 2000. All right. But there's not much that's changed in track and field. Definitely the training has gotten better. All right. So we see the women's times here. All right. So I'm a curious person. I want to know, what are the men's times going to look on the same graph? So we could have something to, compare that to. So we'll activate the stat plot for the men. All right, so I have that in plot 3. All right, L6 was the year, and L7 was the time for the men. All right, got to turn that on, otherwise it's not going to work. And also, I'm going to do a zoom 9 to get them back on the same graph, and so it resizes it for me very nicely. All right. And so here we can see the men's times. All right, so now this gives definitely a nice discussion piece of saying, hey, what do you notice? What are you wondering about this? All right, so I want to give you guys a second and maybe have some questions that you might think of, or some of the questions that the students might come up with once they see this data.
I love that Dennis had already asked, should we ask how many years until the time is 0? It's a great question.
Ooh. Gene, absolutely. Will women ever get as fast as men? Well, looking at this, all right, how many years before the women beat the men? Oh, I love these questions. because guess what? We're going to explore some of those, all right? The women are improving at a faster rate, all right?
But are they?
Good question. All right, so what we can do here is we can introduce some a regression equation for this data. All right, so what we're going to do is we're going to do that. So we press Stat, all right, and go to Calc, all right, choose number 4 for the linear regression. All right, so if we hit enter on that, all right, so the 2 lists that we're going to first do, I'm going to do the women's list here. All right, so I have to make this list 4 and list 5. Right, there we are. Whoops, list 5 in the next line. There we go, list 5. And then we can store the regression equation right away in the one of the Y lists. Okay, there's 2 ways of doing this. All right.
Do you want X and Y list both to be L5?
Oh, thank you. Thank you. Good proofreading. So list 4, this should be. I apologize. All right. All right, so we press alpha and then trace. All right. And then we can store this in number 1 for Y1. All right. And then we calculate this. All right. And right here, they're giving us the linear equation that's going to fit that data. Right. And so this definitely finally gives some context to that slope. All right. And it's at negative 0.02. What does that mean? All right. So that's kind of a nice, contextual piece. All right. And so kind of look at that, again, does it fit, again, how could you determine what kind of model this is? That's a good question that came up. All right. We could turn the diagnostics on. Yes. All right. I didn't do that right now. All right. And then the piece that I always like to think about is what is this 65? All right. So if we're thinking about the context of this problem, the X is representing the years. All right. So in year 0, the women were going to run the 100 meters in 65 seconds. All right. So again, we got to think about, does that make any sense? All right. So going to do the same thing for the men's graph, and then we're going to put them on the same set of axes here. All right. So again, stat, I'm going to go to calc. And I didn't do that correctly, so I got to go back to stat and linear regression. All right. And here we're going to put the men's year, which was L6. And down here, I had this as alpha L7. And I'm going to put that in Y2. And then we're going to calculate it. And then here we can see how the men's record is progressing at 0.00003 thousandths of a second per year. All right. And again, in year 0, the y-intercept, the men ran the 100 meter at 17.6 seconds. All right. So now I'm excited. I want to see what this looks like. All right. It's going to zoom stat. We have a picture here. All right. And so if we look at this linear regression of both these, your questions were asked about, hey, are these things going to intersect? All right. So what year might these be the same? Right? Because I want to find the intersection points of both these graphs. And so it's not on the screen. So put a window. This would be a great guessing game for your students. All right. This graph goes up to 1998. So anybody want to take a guess on maybe when those two are going to be the same exact time? If the women and the men are going to run the race at the same time? I say 2000 and maybe 2010. All right, let's take a look at that.
Oh, Rudy.
Not yet. All right. So we take a look, maybe 2025. We'll try that one. And then we'll graph it. And that's the power of this technology, is you'll be able to recreate this and check out different ideas, right? And you can just change them very quickly, right? So here we see that the two regression equations are equal down in the lower right corner here. So we want to find out what year that is, all right? So using our second and our trace, all right? And then we're going to go to find the intersection. And we'll go find that. Sean, definitely, is it realistic? It's also a good question. We'll get close. Here's the first curve, second curve, and then the answer is in 2019, both men and women will be running 9.77 seconds, right? Which is kind of nice because we've already passed 2019. All right, so we could actually answer some of those questions. Is it realistic? Did this already happen? All right. And so a couple factors here, right? I didn't enter the data of Usain Bolt's world record times, right? I only entered it up until I think 1996, right? So there's a couple more records available. This year here, 1988, that was the last time a woman broke the world record. That's Florence Griffith Joyner and her time of 10.49. And I don't think anybody's actually come close to running that time since, all right? So again, kind of an interesting way to go back and forth, get that prediction, get kids to say, hey, is this possible? All right, to be able to run this fast. Are they both going to run that fast? And then if we take a look, are the women going to exceed the men in the future? Right. So again, I just think that sometimes you take a look at data and, types of things like that. So it's pretty, good conversation starter for the students here. So that was one of the pieces.
I gotta say, I love the chat. I love how involved and active everybody is in the chat. The great questions, ideas people are putting in there. And one of the questions from before was, why are you using a linear model? Well, maybe now that we see that, okay, this said it was going to happen in 2019, obviously it didn't. Well, hey, maybe we need to change our model, right? And so this can branch into so many different mathematical conversations that we can explore with students. And the other thing, Brad, that you were just talking about, you didn't include Usain Bolt's time, and you looked at Flojo's time from there. This reminds me of a lesson I observed my statistics teacher teaching. It was a phenomenal lesson, and it was on influential points versus outliers. And so now looking at the data set of just the women, was that time from 1988, was that an influential point or an outlier? Is Usain's data an outlier or an influential point? What's the difference between those? So you can bring this in for that topic too, which I know is a topic that's on the AP stats exam on a very regular basis. So lots of different ways that this one piece of information can be brought in to analyze so many different topics.
Perfect. All right, I'm going to throw this back to you, Todd. There it is.
All right, let me go back to sharing my screen. And then you're going to keep talking, but I'm going to drive the presentation here. So again, there's the data set that we were using and showing again how you can make that progression. So you can do this on the Nspire, and I saw those some people were talking about doing the Nspire. We're going to look at a different data set, similar, related, but not exactly the same here. And so instead of looking at world record progression, now we're going to look at 100-meter winning time progressions. And so I'm going to jump back into the emulator here, bring up this, and move forward to problem 2. All right. So Brad, go ahead.
All right, so we initially just plotted world record times. Here we have a list of the winning time for the competition that occurs every 4 years. And so we have that data set. All right, so we're going to plot those and see how that progression shows as well. All right, as far as the men and the women. All right, and now the interesting piece about this data set is just when you look at, all right, okay, Todd, you're going to plot them year versus. Okay.
So if you haven't played around with spreadsheets and the data and stats pages, so all of these points are what was on the spreadsheet from before. And so if you want to plot the men's times over time, you can easily do that on the y-axis. And one of the things that I think is great is the ability to either right-click if you're using the emulator or control menu to get the contextual menu on the handheld, and you can add additional y variables. So now we can put men and women against each other on the same data stats page that was from that spreadsheet that we had before.
Which is just what we did with the 84, but we actually had to utilize 2 stat plots for that. All right, so what Todd's going to add here is he's going to add the regression equations for these. And again, we talked about, someone asked, is it a linear regression, or is it could be something else? So we're going to go with, I teach algebra, so everything's a linear regression in algebra. But, we're going to take, we have to get that blurry line of saying it kind of looks linear. And the neat thing about these two is take a look at the slope of both of those. So they're a little, they're much more similar than that last example we had. All right. So we could also talk about, hey, when is that competition going to have the same time? All right. So, we're going to kind of go quickly through this because it's very similar to the last one. So Todd, we could we have both those equations. Is that correct?
Yeah, and we'll show that in just a second. There's some interesting historical data here too that you can use the information for. We've got this data time from 1936 for men and women. Then we have this data time from 1948 for men and women. We got nothing in between there. Why would that be? There you go. You can also look at, well, the men's times go back all the way to 1896, which is when the modern Olympics restarted. The women don't have time until 1928. Why is that? So a lot of different areas that you can begin to explore, again, just from the data set. All right, so yeah, so we have the equations here. And so then the next thing that I did was I inserted a graphs page. And so here's that. There's no graph.
There's no graph. All right, so this is another example where you can talk about your domain, your range, your scales, right? Which is, I think, an important piece that sometimes can get overlooked as far as, you know, it's plotted there, but you can't see it. All right, so we could change that to be able to fit them with a window, or we could probably do a quick zoom fit or a zoom stat. Again, probably not the best model there, but we do have the two equations there, right? And again, it's fitting their y-intercepts, which is kind of an interesting concept. Zero.
Ooh, what does zoom stat do?
So zoom stat will definitely fit the data in the statistics, but it's going to sometimes not fit it the way you want. Right. So again, it's not a fail-safe from time to time. So
where is that on here?
Zoom stat. Oh, it might not be in this one. Data, zoom data. There it is.
So zoom data brings you these two graphs here. One of the questions that somebody asked before about when will these times be the same? Well, again, as we're exploring systems now using the Nspire, as opposed to the 84 CE, just a different device to use it with, that question is great. You give the kids these graphs, obviously you don't see the intersection point. So now, again, it's a good time to go back to, all right, let's make sense of this data. So with making sense of this data, what should we make the window to? We can change the window to go ahead and do that. As math and science people, I'm sure you understand how we can make that happen, but we want to show you some different ways that you can analyze and find the intersection.
Right. So one of the things that came up is you can do there's many ways of getting the intersection of these two lines. We could do a system of equations, system solvers, and then I just discovered this one. I didn't know it existed, but there's a command on the Nspire called nsolve. Right. So if we choose that, I guess it's algebra and numerical solve. Oops, there it is, numerical solve. And the neat thing that I found here was without typing in the equation, I'd said, well, you have equation in F1 and equation in F2. So we're just going to do F1 of X equals F2 of X. And we're solving for, or with respect to X. All right. And according to this data, they will run the same time in that 4-year competition, the year 2300, right? Probably not going to be around for that, but I want to know what the winning time is in that particular year. All right, so Todd's going to do F2, open parenthesis, and then he's going to cut and paste, or he can just type in 2300 either way. And we're going to find out what the winning time is. It's going to be 5.8 seconds for the 100-meter dash, right? And if we want to find it out, we can convert that to how many miles per hour they're running. I guarantee it's probably pretty quick.
So this is in meters per second right now, correct? Was the unit that we were using?
That was in meters per 100 seconds, I think. It was 5.8 per 100 meters. So you're going to have to divide 100 by 5.8 to get the meters per second.
So 100 divided by 5.8.
So 17.2 meters per second.
So then one of the things that we can do is inside of the Nspire is this conversion assistant. And back in high school, I had a TI-85, and I loved the fact that the 85, I could do conversions really easily on that. And that really helped me make it through my science classes in high school. Well, the Nspire has that also. And with the conversion assistant, we can come in here and we can choose all of these different units or measurements that we're looking at. And since we're looking at a velocity, meters per second, we want to convert that from meters per second, which we already have, into miles per hour. Then it's taking the previous answer, that's 17.24 meters per second into miles per hour. And that's the amount of miles per hour that these runners supposedly will be running at in 2300 when their times are the same. So again, is that realistic, as somebody said before? Probably not. Somebody running at 38.5 miles per hour. But I think something that we struggle with is, that I struggle with students in physics classes, we talk about meters per second as the primary unit for a velocity, but our students don't really, they don't conceptualize what a meter per second is. They can conceptualize what a mile per hour is. So I try to kind of go back and forth between those two, the meters per second for the solving purposes, but the miles per hour for the visualization, understanding the meaning behind what that number means.
And just to tack onto that unit converter, as a algebra teacher, it's always nice to be able to have the kids figure out that conversion using the fractions and so on. But if you let them loose on that little converter, it's also, they're going to whip out their phones and figure that out. Convert meters per second to miles per hour. It's before you even talk about it. So, all right.
All right, so moving forward, looking at some other physics aspects of this, is one of the things that we commonly do in a physics class is a lot of graphical motion and the study of motion, kinematics. Kinema is the Latin word for motion, so it's the study of motion. And so what we have here is a sample racer, again, data from 100-meter dash, and we have the total time that elapsed at all these different marks. And I had to force a value in here that wasn't zero to get a velocity. So I just put a number in that was relatively close to zero, because now I'm going to have the spreadsheet work for me and calculate the velocity by taking the distance divided by the time. And then I can get the acceleration by typing in an equation to take the change in velocity divided by the change in time. So I can get all of these calculated now for me using this spreadsheet. And so then using data and stats pages, I can start to create the different graphs of distance versus time, velocity versus time, and acceleration versus time. So when we look at a graph like this, now we can start looking at, okay, so what are these runners actually doing? Can we talk about their speed based off of the distance that they were covering? And does their running style change as the race goes on? And so as we're looking at this, I actually do this as a lab with my students where I have them go in the hallway and run down the hallway, and I have people at different distances with stopwatches. We collect all this data, we make this graph. And what you start to notice is that the displacement, or the distance covered over time, is increasing. And then from once you get to a certain point, it's pretty linear from there. And this is for an Olympic caliber racer. With my students, what you notice is you have this linear here for a while, and then they don't have the endurance to finish the race. And so then they start to really slow down. And so then you get this curve here at the end where the distance is decreasing over time. And now you can start analyzing the change in distance over change in time. You can easily also have a velocity versus time graph. And so now from that same data set, you can take a look at their velocity. And you can see that their velocity, this racer, their velocity was consistently increasing over time, but increasing by smaller and smaller increments. And you can take independently a look at their acceleration versus time. So you can see they jumped out of the blocks, and then they had acceleration going on. A great question and a great misconception for students is looking at this graph, is this runner slowing down? And what students oftentimes look at for this is seeing that as the acceleration is decreasing, that must mean they're slowing down. Well, no, they're just slowing down at, they're gaining speed at a lesser rate. And so it's a great way to kind of go back and forth. And what is this graph actually telling us? But before also, like I showed, you can have multiple graphs on the same page. As we start to look at, well, how does the distance versus time graph correlate to the velocity versus time graph? And can we tell the story of what's happening from the graphs? You can now add multiple variables onto this graph. And so you can have the distance versus time and velocity versus time graphs at the same time of the same data set and start looking how one graph coordinates to the other one. So if I'm looking at just the velocity now, I can look at, well, hey, this velocity is staying pretty darn linear here. So that means that they must be moving at a constant velocity. Well, how do you graph constant velocity? Well, that's covering the same distance every second. So you can go back and forth between the two graphs and start analyzing. If you're not even putting numbers to it, you can start looking at this and start making generalizations about what the runners are doing. You can add in that acceleration on the same graph as well, and I'll have all three of them and show that this acceleration is getting really close to zero, meaning since the acceleration is staying pretty close, the velocity to zero, the velocity must not be changing very much. So it's very easy to be able to back and forth between those. And yeah, Gene, I'm going to come back to this point here as we start looking at split times. That shows how important it is for you to get out of that starting block quickly. We can analyze using reaction time to see, does that reaction time really matter? So a great way to bring in some kinematics and the exploration of these graphs back and forth. Somebody brought up exponential. Right, can you create a mathematical model of these runners? You might not be able to if you incorporate this first time in, because that's going to cause a really funky piecewise graph. But maybe if you look from here on, yeah, is it exponential? Is it power? I don't know what it is, but let's start exploring that and digging into it. So great comment that somebody had there. When we start looking at the split times, instead of looking at the total time that the race was going on, now you can start looking at how long it took them to get to a variety of different distances. So this graph here is showing a variety of different men's world records in the 100 with the different racers you had: Carl Lewis, Maurice Green, Asafa Powell, and then we've got Usain Bolt here in column E. And the distance along those 100 meters and the split time it took to get to them. This first row going across here is their reaction time. So the reaction time between when the gun was fired and when they left the blocks for Carl Lewis was 0.136 seconds. For Maurice Green was 0.162 seconds. Maurice Green beat Carl Lewis's record, but had a slower reaction time. You come over here to Usain Bolt, you've got a much longer reaction time. So now you can start plotting these against each other, and you can start analyzing, well, how did one racer fare against the other race, as we're looking at their distance they covered versus their split times. And if you look just at Usain Bolt, you can see this red dot go up because of the fact that he slowed down celebrating and still was able to master these times and destroy all the rest of the competition. So a lot of fun ways to look at the same data sets between the 84 and the Nspire. And if you're looking at a tabular view for this, you can see all the different times this data set will be made available to you, and looking how Usain Bolt was able to reach a split time that nobody else was able to get to and maintain that for a longer period of time than the runners. So a lot of different things of what is important for that race and be able to win or set a world record in those races.
And one other activity that you could use with that as well, all right, is using that table, trying to create the world's fastest time possible if you morphed all those world records together. What would be the fastest time that these guys could cover? And just to tack on to what Todd was saying, because we're trying to get to one more activity before we run out of time today, was Gene mentioned about getting out quick. All right, sometimes the surprise is going to be in this slide right here. This is distance versus velocity. All right, I believe this might have been Carl Lewis's time. So if you look at about 60 meters in, he reached peak velocity, and almost everybody is decelerating as they're crossing the finish line. It might not look like it. All right, these guys are flying down, or the women are flying down the 100-meter stretch. However, they are decelerating to a certain point because they can't maintain that velocity for longer than a certain period of time. The thing that set Usain Bolt apart was he was able to do it for a longer period of time.
And we show that on the Nspire. Here's a slide also to show the same data set put in, creating the same thing on the 84 CE. So based on the technology available to you, you can do either one of these back and forth. I'm going to quickly, because we're running out of time here, go through some parametric equations as well that we can do. So let me pull this one up. As we talk about parametrics or we talk about quadratics, we have the problems for students where we're asking them how long is something in the air, how high does it reach, these kind of problems. If we're just asking those without a lot of context, or oftentimes the problems, I don't mean this to be offensive, but in math books are oftentimes very unrealistic. Somebody throws the ball at 400 feet per second to begin with. if you can make this grounded in something real, it makes a lot more sense. So we can look at this graph and take a look at, well, all right, so if we change one of these for the parametric equations, the initial velocity in feet per second, okay, that changes some things. And if we change the angle that we launch at, all right, that changes some things. But if we put that same graph onto a picture of a long jumper, well, now we can start to see, well, how does this parametric equation actually relate to what a person is doing? And so now we can try to figure out, well, how fast did this person actually jump? And you can change with the sliders here to show how fast maybe they were going or what angle they jumped at. And maybe if they jumped at a different angle with that same velocity, how would that change the angle they were able to go at? So this is what sports science is doing, is looking at this video analysis and figuring out, hey, if we change this minor thing where we have you jump at a slightly higher angle, we can increase the distance you get to by this amount. Or if we can get you to generate this amount more initial velocity and you jump at that same angle, or less velocity and jump at the same angle, look at the differences that are making. So now this brings so much more context to what we're doing with our students. Another thing that you can analyze now that baseball is back in the Olympics, softball has been there, is you can start looking at exit velocity and home runs, and are they going to match? And so this is an activity here, again, using parametrics, but you have the initial velocity in feet per second, the launch angle, two things that are very, very common. We're using feet per second because we're using the feet per second squared acceleration that is oftentimes used in like an Algebra 2 class. And then C being the initial height that you hit the ball from. And then what we did is we put in a piecewise function of where the outfield wall is. So for example, this is straightaway center at Wrigley Field. So it's 400 feet away and the fence is 11.5 feet high. So if this person were to hit the ball with an exit velocity of 120 feet per second at an angle of 30 degrees, they're not going to hit a home run. But if they launch at 35 degrees, now they can hit that. And so what's cool about this too is you can easily change the piecewise function to be different ballparks around the world. So by changing this equation from 411.5, we can change this to Brad's favorite ballpark, Fenway, and we can have the Green Monster at 310 feet.
Nice joke. That's a Yankee Stadium.
37 feet tall. And now how does that same hit play in this field? So you can start changing fields around. So again, as we're bringing in different data sets and different ideas we can use with students, then here's another sport, another way that we can change and take a look at how this brings in more of a real world setting. Now, this doesn't take air resistance into effect. This doesn't take, is the wind blowing in, the wind blowing out? That brings in a whole other complex mathematics and physics. But a general idea of how does the initial velocity and launch angle impact a home run that could or may not be hit. And Brad, we've got 2 minutes left in this, so I don't know if we need to turn this back over to Mike at this point.
I think we do.
All right, so there's one more activity before we turn over that I'm not going to show you, but it's using images, geometry pages to also do this. So many different ways that we can explore this, and there will be some documents and information that was sent out for you guys. So Mike, let me turn this back over to you.
Thanks so much, Todd and Brad. As we wrap things up, if you have any last-minute questions, feel free to get those asked in the Q&A window. I know Todd and Brad will do their best to give them answer. I know we don't have a lot of time. We'd love for you to continue the conversation. As I think both Todd and Brad mentioned, there was just some great comments and questions rolling through the chat window tonight. Free to, again, get those out on social media and continue that conversation. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed as a link for the documents from tonight's webinar. If you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. And if either of those links aren't working for you at the moment for any reason, hang tight. You'll automatically get a follow-up email within a few days, and that follow-up email will contain a link to the certificate, the documents, and the recording as well, so you can watch this at your own pace. If you have any last-minute questions after the webinar, feel free to give us a call or drop us an email. We'd love to hear from you. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, and we really hope you'll share your thoughts in that post-webinar survey. Huge thanks to Brad and Todd for all the time they put in tonight's webinar. Thanks so much for putting all that together. It's actually, I'm getting excited to go back to school and share this with my students. And thanks everyone for joining us tonight. We hope to see you back online next week. Have a great night.